Hi, welcome to Introduction to Haskell Programming. What is Haskell? Haskell is a functional programming language in which programs are mostly just function definitions, and these are direct and succinct transcriptions of mathematical definitions. There is no need of an elaborate machine model to understand computation. These are some of the aspects or features of Haskell. And most importantly, computation is just like simplifying mathematical expressions. We will see examples in a bit. And many features of Haskell are part of more mainstream languages, even though Haskell may not be as widely used as some languages like Python and so on, or Java. Those all have features that are that originally were developed in functional programming languages. So what is functional programming? There is no definition as such. There is no clear-cut definition as such as to what is functional programming, but it is best understood as a style of programming, and it should be understood in contrast with other styles of programming. The most prevalent style of programming is what is called imperative or procedural style, and this also includes some aspects of object-oriented programming. Let's look at an example. Suppose I want to compute the sum of all numbers from 0 to n. Mathematically, you would express it using this symbol, summation of I, where I ranges from 0 to n. Okay. Let us see how you would program this in a language like C. Let us say you would write a function sum up to. Let's say that is the name of the function. This int here is the return type. This int n is the argument, and the body of the function is something that you might all be familiar with. You declare a variable sum, you initialize its value to 0, and then you run a loop. For I ranging from 0 to n, you repeatedly add I to sum. Okay, so this is the most important part of the program. Sum equals sum plus I. What is happening here is that the value stored in the variable sum keeps getting modified. Finally, you will return the final value of sum after running the loop for n iterations. Just to emphasize, so this program describes a process to compute the sum. It says have a storage location where you initially store 0, keep modifying the value in the stored location, and by adding I repeatedly to the value in that location. Yeah, so there is a repeated change of state, as it is called. The state here is the value stored in the variable sum. Okay. This is the usual style of programming. Let's see how you would do this in Haskell. So as I mentioned earlier, functional programming is a style of programming in which the basic method of computation is applying functions to arguments. The basic unit of programming here is a function definition. Let us look at how we would elaborate the ... in 0 plus 1 plus ... plus n. Earlier we just left it loose even in the mathematical definition, but we can formalize it and make it more precise by defining it this way. And this is a standard definition in math. This is the standard way in which you would define summation from 0 to n in any basic mathematics textbook. Summation of I ranging from 0 to 0 is 0. Summation of I ranging from 0 to n is summation of I ranging from 0 to n minus 1 plus n. Okay. So there should be an I here. Yeah, this should be so this is the code for this is the definition for summation of I from 0 to n. And in Haskell and many other functional programming languages like ML, OCaml and so on, you would directly transcribe the above definition into code. As you can see, unlike the earlier definition where in C, where we had a function with some input type and a return type, and the body of the function was defined. A function is given by its return type, the parameters, its name, and the body, whereas here it is just like a mathematical definition. So sum up to is a function. You define what its value is for 0, and you also define what its value is for n which is not 0, and you see that there are two lines of definition. This is the base case, and this is the inductive definition. Right. So sum up to 0 is just 0, sum up to n is sum up to n minus 1. This is what you may know from other programming languages as a recursive call. And then you call sum up to with argument n minus 1 and you add n to it. So this is just an indication of what functional programs look like. We will look at Haskell in more detail. Let us just set out the course aims in brief. So we want to teach algorithmic problem solving, but in a functional style, and we will see how to transcribe mathematical or logical problem specifications into functional programs. We will also look at common data structures and their analysis. We will also look at basic algorithms for sorting, searching, etc. Maybe some graph search algorithms. We will also look at structuring large programming tasks using some advanced Haskell features towards the end of the course, but these three agendas form the main part of the course. Let us delve a little deeper into functional programming. Let us look at what a function is. Let us just refresh our ideas of what a function is. A function takes one or more arguments, returns a single result. You could return multiple values as a result, but you should pack them in as a pair or some value like that. We will see later how you can actually return a pair of values, but it is still considered a single result, a single value. And a function definition is just an equation with a function name, argument names, and a body. Right? For instance, here is a function definition. Double is the name of the function. This is the arguments. This is the body of the function. Yeah, double x just adds x to itself, so it returns the double of x. Notice that this is almost like a mathematical function, but there are a few differences. In mathematics, you would write something like this: double of x. Yeah, you would write the function name, you would write the argument within parentheses. Okay, whereas in Haskell, you write double followed by a space followed by a equal to symbol and then the definition. Notice that this equal to symbol, equal to is not people who are used to programming in other languages, you are familiar with the equal to symbol used for assignment. What is assignment? Assignment is like the C program I showed before. Yeah, here this is an assignment. This changes the value whereas equal to in functional programs roughly it binds a value or a definition to a name. Okay, that's all. It is just saying let me call x plus x by the name double of x. Okay, there is no variable here that is being modified. Okay, so that's an example function. How do you apply functions? You apply functions just like you define the function here. You say the function name and you write a space and then you give the argument. So double of 3. And what is computation here? Computation is replacing the actual arguments in place of the argument names in the body. So double of x, so if 3 is the argument, then it becomes 3 plus 3. Where in the body, wherever you see x, you will replace it by 3. That's all. This is all you need to understand about applying functions for the major portion of the course, at least half the course, right? So, and 3 plus 3 simplifies to 6, okay? So, in some sense, these are computation is like simplifying expressions. Here is a longer computation, double of 2, you can simplify the inner double 2 and get 2 plus 2, and 2 plus 2 simplifies to 4, so you have double of 4 is 4 plus 4, so you get 8. Or you can follow an alternative route, computations need not be unique. Instead of simplifying the inner double, you can instead of simplifying the inner double, you can simplify the outer double. So double of anything is that thing plus that thing. So double of 2 is double of 2 plus double of 2. And then you simplify each of these double 2 in turn. So this is 2 plus 2, that is 4. And then this double 2 becomes 2 plus 2, which is 4. Finally you have 8. Okay. But as you know from high school arithmetic, in many cases the alternative ordering of computation doesn't make a difference. I could, for instance, say 2 plus 5 into 3 plus 7 equals 7 into 3 plus 7 equals 7 into 10 equals 70, or I could also say 2 plus 5 times 10 equals 7 times 10 equals 70. Doing it in different orders doesn't change the final value. This is an important fact about Haskell too, and Haskell makes very good use of it, as we will see later. So, for some reason this is wrong, this should be Haskell. So, Haskell is a programming language for describing functions, and typically a function description has two parts: type of inputs and outputs, and definition or rule for computing outputs from inputs. We have not seen types so far. Here we are introducing types for the first time. Here is another example function, square. Its type is int arrow int, and notice here that this is very close to how you would write types in mathematics. You would write, for instance, things like sine is a function from complex numbers to complex numbers, maybe, yeah, or and so on, right? Or you might say floor is a function from reals to natural numbers or reals to integers. Right? You could write all this, and the arrow is used to denote the function type. So similarly in Haskell also you denote the type of a function by writing arrow. You put the input type before the arrow and the output type after the arrow. This is the type specification, and the computation rule is just this, that square of x is x times x. Okay. So I could have things like square of 5, and how do you compute this? You just replace x by 5 in the body. So this is just 5 star 5, and there are built-in simplification rules that will take this to 25. But you could also do something like this: square of double of 2 square of double of 2 is square of 4, which is 4 times 4, which is 16, or you could say this is double of 2 times double of 2, which is 4 times double of 2, which is 4 times 4, which is 16. Yeah, you could do computations like this. But the important point is that a function definition is specified by specifying its type, and the type is specified by writing an arrow and putting the input types before and the output types later. And then you give the computation rule. You say square on some argument whose name is x will be x times x. Okay. So what are the types in Haskell? So you have int, which is on most modern machines it will be 64-bit integers, but if it's an older machine it will be 32-bit integer, or maybe some phones it will be 32-bit integers. And int has these operations: plus, minus, star, slash. Slash denotes division, and slash produces a floating point value. So 5/2 will give you something like 2.5. And you also have div and mod. Div produces only integer values. So 5 whereas mod 5/2 is 1. Importantly, these are the integer int type has a bounded range. So there are two values, min bound and max bound. For most bounded types, you can use min bound and max bound to find the minimum value and the maximum value for that type. We will see this in the demo in a little bit. You have floating point numbers. You also have another type called double. These are all floating point numbers. We will see them a little bit later. Characters are given by writing it within single quotes like this. Okay. So A, B, etc. 0, 1, etc. Actually, Haskell by default allows Unicode characters, but we will mostly stick to ASCII in our examples. You can play around with this. Integer is unbounded integer, so you actually have large integers which are limited only by memory resources. We will see examples in a bit when we go through the demo. Another very useful type is bool, which is the type of booleans. It has exactly two values, true and false, and it has the operations and, or, and not. And or are given by the following truth tables. These two are the symbols that are typically used in mathematics, but here in programming you use these symbols. So if it's if both inputs are false, then both and will give a false value, or will also give a false value. If A is false and B is true, then AND will give you false, OR will give you true. Similarly, if A is true and B is false, the AND of their values will be false and the OR of their values is true. Finally, if both values are true, then both AND and OR are true. So this is the definition of AND and OR. Not typically in mathematics you will use the symbols, these are symbols that are used. In programming you use the symbol not, right. So not maps false to true and true to false. Then you have relational operators that compare two integers, two floating point numbers, two characters, etc. So these are equal to, which you write with two equals, Slash equals is for not equals to. This is very close to the mathematical notation. Less than or equal to, greater than or equal to. Okay. All these produce Boolean values. So I can say 5 less than or equal to 3, and that will produce false. Let's look at some more function definitions. XOR. XOR is a function that is usually denoted by this in mathematical notation, and this is how the function is defined. If the two values are different, then their XOR will be true. If the two values are the same, then the XOR is false. So the input is two values of type bool. So this is important. Here, if there are two inputs, then you will write an arrow as before, and you will, this is the output type. These two are the input types. In general, if I have 5 inputs and 1 output, let's say 5 integers are inputs and 1 character is the output, then I will write 5 times int. I will write the output type here, and I will put arrows in between. Why am I doing it this way? We will see. This is a nice feature of Haskell. We will see why we do it this way in a couple of lectures. Let's look at the definition of XOR. XOR of B1, B2, I said XOR will be true if B1 is true and B2 is false, or if B1 is false and B2 is true, which we have written as an expression here. In either of these two cases, XOR will be true. If neither of these cases holds, then XOR will be false. Let's look at another definition. Is ordered. There are 3 values of type int. Those are the inputs, and the output is a Boolean. The function checks whether the 3 inputs are in order. So is ordered XYZ is nothing but saying x less than or equal to y and y less than or equal to z. So it returns a Boolean value, but once again you see that I have written 3 ints. I have written a bool, which is the output type, and I have introduced arrows in between. So we have looked at some basic examples. We will go through more details in the next lectures, but it is fine to write all these expressions, all these programs. How do we run them? Okay. So to run Haskell programs, you need to use what is called GHCI. This is the program. GHC stands for Glasgow Haskell Compiler. It is open source. One can download. I'll probably tell you how to download it for Windows. And I stands for interactive or interpreter. Okay. And basically you can interactively call built-in functions and load user-defined Haskell code from a text file. It is very similar to how Python works. So you can either load functions that you've written saved in a text file, or you can use it like a calculator and try to run built-in functions. So it is available for Mac OS, Windows and Linux. Okay, so how do you use GHCI? We will show a demo in the next lecture, but you create a text file with an extension .hs with your Haskell function definitions, run GHCA at the command prompt. I am assuming that you are all familiar with running the command prompt on Linux or Mac OS or the PowerShell in Windows. And inside GHCA you can say :load myfile.hs, that will load your file into GHCA, and you can actually write expressions which you have defined in your file, and they will give the appropriate results. You can also write standalone Haskell programs. We will see that also, just a brief example, but we will talk about standalone Haskell programs much later in the course. In the first lecture, I just wanted to show you an example of a standalone Haskell program. So, standalone Haskell programs require a main function, and here is a simple hello world program in Haskell. Yeah, so you can write it as hello.hs, and this is just a command. We will explain this command much later, several lectures later. The various keywords that are, the various function names that are used here. Put string line is a function that puts a string on the output device, whatever it is, your screen most probably. And but how do you run a standalone Haskell program? You compile such programs using GHC, that's another command, and GHC hello.hs will produce an executable named hello, or if you are using a Windows machine, it will produce an executable named hello.exe, and you can run the executable by issuing ./hello from the command line. This is for Linux and Mac OS. On Windows, you would say ./hello.exe. We will concentrate on GHCA for most of the course, but in the later half, we will sometimes look at compiling with GHCA and GHC and running standalone programs also. Now, as you follow this course using the slides that we upload and the videos here, you also have lots of excellent resources for Haskell. The official Haskell page, I think this is a clickable link, you can just click here and I am trying to open the Haskell page in Chrome. So, this is a book, Programming with Haskell by Graham Hutton. Here is another book, Introduction to Functional Programming Using Haskell by Richard Bird. Here is another book, Thinking Functionally with Haskell. These books are reasonably easily available, but you have to pay for them. But there are some online books which are available for free. This is a book, Real World Haskell. Once again, there is a website for that. Here is another online book, Learn You Haskell for Great Good. And this is not an online book, but it's a huge book, Haskell Programming from First Principles, which covers quite a lot of material. There is a nice YouTube playlist for Haskell for imperative programmers. If you have experience with other programming languages and you are new to Haskell, you can go through this playlist and it might supplement some of the material that I teach in this course. There are plenty of other resources that you can find if you search on the internet. So, yeah, thanks for listening to this lecture. In future lectures, we will look at other aspects of Haskell. Thank you.